What if everything you see, everything you feel, everything you have ever known is not real? What if the stars that burn in the night sky, the ground beneath your feet, even the very atoms that make up your body are not material in the sense we think, but instead lines of code executing silently within a cosmic computer? It is a question that stretches the mind, challenges intuition, and unsettles the deepest corners of human thought. And yet, in 2003, philosopher Nick Bostrom presented a framework for considering this possibility not as science fiction, but as a logical consequence of technology, computation, and probability. He suggested that the universe we inhabit might not be the original, base reality, but a highly sophisticated simulation, so detailed and so precise that its inhabitants, us, could never detect it. Every memory you hold, every thought you believe is uniquely yours, might in fact be a product of computation, an emergent property of code running on a machine beyond human comprehension. To grasp the depth of this idea, we must first look back at the origins of our inquiry into machines, computation, and intelligence. In 1950, British mathematician and logician Alan Turing asked a deceptively simple question: can machines think? At the time, computers were enormous, room-filling machines capable only of arithmetic and basic calculations. The idea that a machine could exhibit intelligence or even consciousness was considered almost fantastical. Yet Turing proposed a test, later called the Turing test, to determine whether a machine could convincingly emulate human behavior. This concept planted the first seed of a radical possibility that thought itself, the essence of consciousness, could be represented as computation. By the 1960s and 1970s, computing technology had advanced enough to simulate complex systems. Early computer models could replicate weather patterns, population dynamics, and even simple ecological systems. Video games emerged as a demonstration of digital worlds governed by rules. Blocky landscapes, characters with limited autonomy, and predictable physics. But these early simulations were just the beginning. They showed that a universe, or at least a part of one, could be constructed artificially, with laws and interactions defined mathematically. And if we extrapolate this trajectory into the future, it becomes conceivable that a civilization with sufficient computational power could simulate entire universes, with sentient beings living within them, utterly unaware of the artificial nature of their reality. Bostrom's simulation argument formalized this astonishing possibility. He proposed a trilemma. One of three statements must be true. Either most civilizations at our level of technological development go extinct before they can create ancestor simulations, or they choose not to run such simulations, or we are almost certainly living in a simulation right now. The logic is deceptively simple. If technologically advanced civilizations can create countless simulated realities, then the odds that we inhabit the original base reality shrink dramatically. We may be statistically a product of simulation rather than the product of a natural, unsimulated universe. The thought is dizzying. Every law of physics, every flicker of light, every decision and consequence could be encoded by unseen programmers on an unfathomable machine. To make this more concrete, consider the digital worlds we experience today. In video games, characters move and interact according to rules that the player cannot alter. They make choices, respond to threats, form alliances, and sometimes fail in ways that appear unpredictable. In virtual reality, we can inhabit worlds that respond to sight, touch, and sound, creating the illusion of a tangible environment. Now imagine scaling this technology billions of times beyond anything humanity has yet achieved. Imagine a universe simulated down to the smallest quanta, with every particle, every photon, every ripple of energy calculated in real time. In such a universe, consciousness could emerge naturally from complex interactions, leaving its inhabitants, like us, convinced that their experience is real. Yet this idea is not just philosophical speculation, it has empirical consequences. Some physicists suggest that the universe might bear subtle signs of its computational nature. Why do the fundamental constants of physics appear so precisely calibrated for the existence of life? Why do quantum particles behave differently when observed, collapsing from a wave of probabilities into a single determined state? Why does the universe expand at a rate that allows stars, galaxies, and planets to form? Could these be hints, tiny fingerprints of an underlying computational structure? Could the universe itself have limitations, resolution constraints, or even glitches like a digital simulation? The philosophical implications are profound. If we are simulated, what does that mean for consciousness, free will, morality, or the meaning of our existence? Are we merely emergent patterns in a program, or does the program itself possess intelligence, intention, or purpose? And if a civilization is capable of creating such simulations, what does it say about our own potential? Could we one day become the architects of universes, generating simulations indistinguishable from our own reality? Even the history of human thought echoes these questions. Over 2,300 years ago, Plato told the allegory of the cave, where prisoners chained inside a dark chamber mistake shadows on the wall for reality. Only when one prisoner breaks free and steps into the sunlight does he see the world as it truly is, three-dimensional, vibrant, and far more complex than the shadows on the wall. Plato's allegory was more than a story. It was a warning that human perception might be limited, that reality could be far richer, stranger, or more artificial than it appears. Centuries later, Descartes posed an even more unsettling thought. What if every sensation we experience, every memory we hold, every understanding of the world is being manipulated by an external force? He imagined an evil demon, a being of such power and cunning that it could deceive our senses perfectly, crafting an entire illusion of the world so complete that we could never detect the deception. Descartes' question was existential. How can we ever know that anything we perceive is truly real? These early explorations planted the seeds of skepticism, teaching us that reality may not be as solid as we believe. The philosophical groundwork laid by Plato and Descartes provided the framework for later thinkers to explore the possibility of artificial reality in more concrete ways. Fast forward to the 20th century, when advances in computing transformed abstract ideas into practical experimentation. In 1950, Alan Turing proposed the question that would change everything. Can machines think? Computers were enormous, room-filling machines capable only of arithmetic and basic calculations. The idea that a machine could exhibit intelligence or even consciousness was considered almost fantastical. Yet Turing proposed a test, later called the Turing test, to determine whether a machine could convincingly emulate human behavior. This concept planted the first seed of a radical possibility, that thought itself, the essence of consciousness, could be represented as computation. By the 1960s and 1970s, computing technology had advanced enough to simulate complex systems. Early computer models could replicate weather patterns, population dynamics, and even simple ecological systems. Video games emerged as a demonstration of digital worlds governed by rules, blocky landscapes, characters with limited autonomy, and predictable physics. But these early simulations were just the beginning. They showed that a universe, or at least a part of one, could be constructed artificially,
with laws and interactions defined mathematically. And if we extrapolate this trajectory into the future, it becomes conceivable that a civilization with sufficient computational power could simulate entire universes, with sentient beings living within them, utterly unaware of the artificial nature of their reality. Bostrom's simulation argument formalized this astonishing possibility. He proposed a trilemma. One of three statements must be true. Either most civilizations at our level of technological development go extinct before they can create ancestor simulations, or they choose not to run such simulations, or we are almost certainly living in a simulation right now. The logic is deceptively simple. If technologically advanced civilizations can create countless simulated realities, then the odds that we inhabit the original base reality shrink dramatically.
As we continue this journey, we will explore the evidence, experiments, and paradoxes that hint at a simulated universe. We will examine cosmic anomalies, quantum peculiarities, and technological projections that suggest our universe may be less a physical space and more a grand computational masterpiece. And along the way, we will confront questions that have haunted humanity for centuries. What is real? What does it mean to exist? And could the universe itself be a creation, designed and maintained by intelligence far beyond our own? The journey has begun. The shadows on Plato's cave wall have shifted, and the first glimpse of a digital universe beckons. What we are about to explore may forever change the way we see the cosmos and ourselves within it. If reality is a simulation, then it must run on some kind of computational substrate. But what would that entail? How could a universe with billions of galaxies, countless stars, and unimaginable complexity be calculated in real time? To answer this, we must first explore the history of computation and the trajectory of technological advancement. In the mid-20th century, computers were gargantuan, room-filling machines capable only of simple calculations. Yet even then, scientists dreamed of scaling these machines to simulate complex processes. Moore's law, formulated by Gordon Moore in 1965, observed that the number of transistors on a microchip doubles roughly every 2 years, effectively doubling computing power at an astonishing pace. This exponential growth hinted at a future in which computational capabilities could reach levels inconceivable to our ancestors. If the trend continues, the amount of computation available to an advanced civilization could be sufficient to simulate not just planets or galaxies, but entire universes populated by conscious beings. By the 1980s and 1990s, simulations became more sophisticated. Researchers could model weather systems, ecosystems, and even simple social interactions. Video games demonstrated worlds governed by rules, where digital characters made decisions, adapted, and sometimes failed in ways that seemed spontaneous. Virtual reality allowed humans to inhabit immersive spaces, tricking the senses into accepting digital input as real experience. Each of these milestones represents a proof of principle. The universe itself, with all its complexity, could potentially be represented digitally if the computational resources were sufficient. But the challenge of simulating a universe is immense. A full-scale simulation would require not only vast computational power, but also an understanding of the fundamental laws of physics, from quantum mechanics to general relativity. Every particle, every photon, every force must be modeled with exquisite precision. The smallest errors could propagate, creating inconsistencies or glitches, just like a video game can crash if its physics engine fails. Yet nature itself may provide clues. Some physicists speculate that the universe is discrete at the smallest scales, quantized in ways that could be analogous to the pixels on a digital screen. The Planck length, approximately 1.6 times 10 to the negative 35 meters, represents the smallest meaningful unit of space, and the Planck time, about 5.39 times 10 to the negative 44 seconds, the smallest unit of time. These limits suggest that the universe may not be continuous, but computational, with fundamental resolution constraints. Quantum computing further complicates and enhances this picture. While traditional computers process information sequentially, quantum computers leverage superposition and entanglement, performing multiple calculations simultaneously. This could, in principle, allow the simulation of systems far more complex than conventional computers could manage. A civilization with access to quantum computational frameworks could simulate entire universes with remarkable fidelity, encoding laws of physics, biological evolution, and even consciousness itself into their digital construct. The concept of nested simulations also emerges from this perspective. If one advanced civilization can simulate universes, it is conceivable that beings within that universe could eventually develop their own simulations, creating a hierarchy of nested realities. Each layer of simulation may be indistinguishable from its parent reality, just as humans cannot distinguish between the real world and a highly immersive virtual reality game. The implications are staggering. If simulations can contain simulated beings, who themselves create simulations, then the number of simulated realities could vastly outnumber the original, base reality, making it statistically likely that we ourselves inhabit a simulation. There are practical computational limits to consider. Information storage, processing speed, and energy requirements impose constraints on any physical computer. Yet the universe itself may be designed to work within these limits. Some researchers propose that phenomena such as the speed of light, the maximum energy density, or even the probabilistic nature of quantum events may represent optimization strategies, allowing the simulation to run efficiently without overwhelming its computational substrate. In this view, what we perceive as the laws of physics may also be the rules of the program, the algorithms that maintain stability and coherence across the simulated universe. Recent theoretical work explores this further. Physicist Seth Lloyd at MIT has suggested that the universe itself could be considered a quantum computer, processing information at an unimaginable scale. Edward Fredkin proposed digital physics, suggesting that reality is fundamentally composed of information rather than matter. These ideas provide a bridge between philosophy and empirical science. If the universe can be interpreted as computation, then our experience of space, time, and causality might be the emergent behavior of underlying algorithms. Even the concept of randomness may have computational explanations. Quantum mechanics appears probabilistic, with particles collapsing from a cloud of probabilities into discrete states only when observed. In a simulated universe, such behavior could reflect an efficiency strategy. Why calculate every detail until it is observed? This would conserve computational resources while preserving the illusion of continuity. Similarly, the cosmic microwave background, the faint afterglow of the Big Bang, exhibits irregularities and patterns that some theorists speculate could hint at a discrete, grid-like structure beneath the apparent continuum of space-time. The convergence of computational theory, physics, and philosophy challenges the way we understand reality. From Plato's cave to Descartes' evil demon, humanity has long questioned the nature of existence. Now, with the development of quantum mechanics, computational theory, and virtual environments, these questions take on a tangible form: the possibility that the universe itself is a simulation, governed by rules, constrained by computational limits, and optimized to produce consciousness within a controlled environment. Our technological trajectory mirrors this possibility. As humans, we have gone from simple calculators to complex simulations of ecosystems and galaxies. We are beginning to model life itself,
creating artificial intelligence capable of learning and evolving. If this is the path we follow, it is not inconceivable that a future civilization, ours or another far more advanced, could simulate entire universes with conscious beings who are unaware they are part of a program. The challenge for us now is both theoretical and empirical. If we are living in a computational reality, can we detect it? Are there clues embedded in the laws of physics, the behavior of particles, or the structure of the cosmos that betray the nature of the simulation? And if such evidence exists, what would it mean for our understanding of reality, consciousness, and the universe? The questions are immense, the possibilities staggering, and the answers, if they exist, may change everything we believe about life, the cosmos, and ourselves. We have begun the journey, exploring the intersection of computation and existence. What lies ahead is an exploration of observable signatures, anomalies, and paradoxes that could reveal whether the universe is real or a simulation. If the universe is a simulation, then it may leave traces, subtle signatures, tiny anomalies that hint at an underlying computational structure. Scientists have long assumed that reality is continuous, infinite, and free of constraints beyond the laws of physics as we understand them. But the deeper we probe, the more evidence emerges of limitations, discretizations, and patterns that could suggest something far stranger, that the universe is running on some kind of cosmic hardware. Consider the quantum world. At the smallest scales, particles behave in ways that defy classical intuition. A single photon can exist in multiple states at once, a phenomenon known as superposition. It is only when measured or observed that the photon collapses.
Then there is the cosmic microwave background, the faint afterglow of the Big Bang. When mapped with extraordinary precision, it reveals subtle irregularities, tiny ripples in temperature and density across the sky. These anomalies have puzzled cosmologists for decades. Could they be natural fluctuations, or might they represent the pixels of a discretized universe, a grid underlying the apparent continuity of space-time? Just as a digital image is composed of individual dots of color, the fabric of reality itself may be composed of discrete units at the Planck scale, forming a lattice on which the simulation operates. Physicist Silas Bean and his colleagues at the University of Bonn proposed a method to detect this lattice-like structure. They suggested that high-energy cosmic rays, the fastest particles in the universe, might reveal limits in momentum distribution if the universe were discrete. Current observations already hint at anomalies in cosmic ray energy levels, suggesting that there could be fundamental resolution limits to space itself, clues that our universe may be digital at the most fundamental level. Other researchers point to the peculiar fine-tuning of the universe as a potential signature. The constants of physics, such as the gravitational constant, the charge of the electron, and the cosmological constant, are precisely calibrated to allow stars, galaxies, planets, and life to exist. Alter these values even slightly, and the universe would collapse into a sterile void. While some explain this through the anthropic principle or multiverse theories, a simulated universe offers an alternative. The parameters may be intentionally set to produce a stable, complex environment capable of supporting conscious life, much as a programmer sets conditions for a video game world. Quantum entanglement adds another layer of intrigue. Particles separated by vast distances can instantaneously influence each other in ways that seem to violate the speed of light. Some theorists suggest that this spooky action at a distance might hint at non-local computation, a mechanism by which the universe can update information across its simulation grid without the constraints of classical space. In other words, entanglement may be a window into the underlying architecture of the cosmic computer, a process that maintains coherence across the simulation. Even the probabilistic nature of quantum events could be interpreted as an efficiency strategy. In a complex simulation, it is computationally expensive to calculate the precise state of every particle at every moment. Instead, the simulation may generate outcomes only when they are observed, a strategy known as lazy evaluation in computer science. This would explain why quantum particles exist as clouds of probabilities until measured, and why the act of observation appears to influence reality itself. Some physicists have also noted patterns in large-scale cosmic structures that seem too regular to be purely random. Galaxies form filaments and walls, leaving vast voids in between. The distribution of these structures is consistent with simulations of digital universes, where rules and algorithms guide the emergence of order from apparent chaos. Could the very scaffolding of the cosmos be a signature of intentional design, a computational backbone keeping the universe coherent and stable? These observable clues, while tantalizing, are subtle. None prove that the universe is a simulation beyond doubt, but they suggest that the laws of nature may not be entirely arbitrary. The speed of light, the quantization of energy, the emergence of order from randomness, all could reflect underlying computational constraints. If the universe is a program, then these anomalies are its fingerprints, hints of the machine beneath the illusion. Consider the implications. If we can detect signs of computational structure in the universe, then reality is no longer an abstract backdrop. It becomes a system we can study, analyze, and perhaps even manipulate. The boundary between physics and information theory blurs. The universe is both a physical space and a computational construct, operating according to rules that may one day be decipherable. Even our everyday technology offers a glimpse of what might be possible on a cosmic scale. Video games render only the visible portion of the world at any given moment, using algorithms to fill in unseen areas when needed. Virtual reality environments create fully immersive experiences with limited computational resources. Could the universe operate similarly, calculating only what is observed, optimizing resources, and creating the illusion of infinite continuity? If so, the very anomalies we detect in physics, the collapse of quantum states, the grid-like structures at the Planck scale, the fine-tuning of constants, may be evidence of a program running behind the scenes. As we explore these clues, the picture becomes increasingly complex and fascinating. Observable signatures point towards a universe that is not entirely free, continuous, or random. Instead, it exhibits patterns, limits, and efficiencies, suggestive of computation. From the strange behavior of quantum particles to the large-scale structure of galaxies, from the cosmic microwave background to high-energy cosmic rays, the universe may be revealing the scaffolding of its own construction. The journey now moves to deeper implications. These observable signatures are not isolated curiosities. They form a tapestry of evidence hinting at something far stranger than previously imagined. Could the universe itself be a vast simulation? Its laws of physics and cosmic architecture shaped by algorithms and code? And if so, what does that mean for consciousness, for free will, for the very nature of existence? The evidence we have discussed so far is only the beginning. It provides tantalizing hints that reality may be computational at its core. But the most remarkable discoveries come when we consider the deeper implications, when we move beyond observation to interpretation and explore what these clues mean for our understanding of the universe itself. The observable signatures we have discussed, quantum peculiarities, fine-tuned constants, cosmic lattices, are only the beginning. They hint at a strange underlying structure, but the deeper we investigate, the more the universe seems to defy expectation, presenting phenomena that stretch the imagination and challenge conventional physics. These are the anomalies that invite speculation, the behavior of consciousness, the paradoxes of quantum mechanics, and the patterns of reality that seem almost intentional. Consider the double-slit experiment. When particles, such as electrons or photons, are fired at a screen with two slits, they create an interference pattern, a wave-like distribution that suggests the particle passes through both slits simultaneously.
But if an observer measures which slit the particle passes through, the interference pattern disappears, and the particle behaves like a discrete particle instead of a wave. The act of observation seems to change reality itself. In a computational framework, this could be a strategy of efficiency. The simulation calculates only what is observed, conserving resources while maintaining the illusion of continuity. Reality, in other words, may be rendered on demand. Even stranger is the delayed choice experiment, an extension of the double-slit setup. Researchers can decide to measure a particle after it has passed through the slits, and yet the particle behaves as if it knew in advance whether it would be observed. Cause and effect appear to break down, suggesting that the universe is not only probabilistic, but retroactively adjustable. In a simulated universe, this could reflect a system designed to maintain consistency, dynamically updating past events to match observed outcomes, a feature familiar to anyone who has played a sophisticated video game or experienced virtual reality, where unseen areas are rendered only when explored. Quantum entanglement amplifies these mysteries. Entangled particles remain connected across vast distances, instantaneously influencing each other regardless of separation. Experiments have confirmed these effects across kilometers, even in orbit around Earth. This spooky action at a distance is difficult to reconcile with the speed of light limit in classical physics. Yet, in a computational universe, entanglement might represent a mechanism for maintaining coherence across the simulated environment, a way for information to propagate beyond the apparent constraints of space. In essence, the universe could be using shortcuts, algorithms to optimize the fidelity of the simulation while conserving processing power. Beyond quantum phenomena, consciousness itself presents deep puzzles. Philosophers and neuroscientists increasingly consider the possibility that awareness is a form of computation. Conscious experience emerges from complex information processing integrated across neural networks. If consciousness is fundamentally computational, then it is theoretically possible to simulate minds within a computer, or, on a grander scale, within a universe simulated by a sufficiently advanced intelligence. This raises staggering questions. Are we, individually, self-aware computations running inside a cosmic program? Could our thoughts, decisions, and perceptions be emergent properties of code executing in a machine far beyond our comprehension? Recent experimental work hints at possibilities that sound like science fiction but are grounded in physics.
The convergence of quantum mechanics, cosmology, and computational theory forces a re-evaluation of everything we thought we knew. Reality appears strange, counterintuitive, and at times almost designed. The anomalies, the limits, the patterns, they form a tapestry that hints at the possibility of a digital substrate underlying existence. It is as if the universe itself is a program, optimized for stability, coherence, and the emergence of consciousness, with rules and constraints carefully calibrated to produce the world we inhabit. These deeper implications shift the question from possibility to probability. Observable signatures are no longer isolated curiosities. They form a consistent pattern that aligns with the simulation hypothesis. Quantum paradoxes, the fine-tuning of constants, entanglement, and the discretization of space-time all point toward a universe that may be computational at its core. If this is true, then our understanding of physics, consciousness, and existence must be reframed. We are not merely observers of reality. We may be components of a system designed to appear real. As we proceed, the journey will expand further, connecting these observations to theoretical frameworks, ongoing research, and potential tests that could one day reveal the true nature of the universe. We are moving from evidence to interpretation, from observation to implication, and the picture that emerges is both awe-inspiring and unsettling. The universe may be less a natural phenomenon and more a carefully constructed simulation, an intricate program whose complexity exceeds anything humanity has yet imagined. The stage is now set to explore the broader framework that ties these anomalies together. the theories, experiments, and philosophical interpretations that could explain the cosmos as computation. What we uncover next will challenge not only science, but the very essence of existence itself. The anomalies, paradoxes, and subtle fingerprints we discussed hint at a startling possibility that reality itself may be computational in nature. But what theoretical framework could unify these observations? How could the universe operate as a simulation without betraying its artificial nature? To answer these questions, we must turn to the intersection of physics, information theory, and philosophy, a convergence that has begun to produce frameworks capable of describing a universe that behaves like code. One of the most compelling ideas comes from the field of digital physics, championed by Edward Fredkin and further explored by physicists such as Seth Lloyd at MIT. Digital physics posits that the universe is fundamentally composed of information rather than matter, that the laws of physics emerge from the processing of bits in an underlying computational substrate. In this framework, particles, fields, and forces are not the ultimate reality. They are the information structures that arise from the processing of discrete units of data, the pixels of existence. Space and time themselves become emergent phenomena, approximations of an underlying network of information processing. This perspective provides a natural explanation for some of the anomalies we've encountered. Quantum superposition, entanglement, and probabilistic outcomes can be interpreted as computational shortcuts, strategies to optimize processing in a universe that is, at its core, a simulation. Observers collapse probabilities into a single outcome because the system only calculates what is necessary, maintaining the illusion of continuity while conserving resources. Fine-tuned constants may be parameters in the simulation, deliberately set to produce stability, complexity, and conscious observers. Even the lattice-like structure suggested by high-energy cosmic ray studies may reflect the fundamental grid, the computational architecture on which the universe operates. The holographic principle further strengthens this framework. Proposed by physicists Gerard 't-Hooft and Leonard Susskind, it suggests that all the information in a three-dimensional volume can be encoded on a two-dimensional surface, much like a hologram. In a computational context, this could be viewed as a form of data compression, encoding the vast universe efficiently while maintaining its observable properties. Black holes, with their information-preserving event horizons, may act as processing nodes, storing and transmitting data across the simulation. In essence, the universe could operate like a quantum computer, processing information at scales that dwarf our imagination, generating the rich complexity we perceive as reality. Seth Lloyd has gone further, proposing that the universe itself is a quantum computer, performing roughly 10 to the 120 operations per second across all matter and energy. In this model, everything, from the orbit of planets to the firing of neurons, is a computation, an emergent result of information processing on a cosmic scale. It suggests a profound unity between physics and computation. Laws of nature or algorithms, particles or data structures, and consciousness may be a phenomenon that arises naturally from sufficient informational complexity. The simulation hypothesis, formalized by Nick Bostrom, integrates seamlessly into this theoretical framework. It posits that advanced civilizations could have the computational capacity to create ancestor simulations, reproducing universes populated with conscious beings. The implications are staggering. If one civilization can produce even a single simulated universe, the odds overwhelmingly favor the existence of many such simulations. In this context, our reality may not be the original universe, but one of countless digital realities, each complete with stars, galaxies, and self-aware inhabitants who perceive their existence as real. Critics argue against the hypothesis, emphasizing Occam's razor. The simplest explanation is often the correct one. Perhaps the universe is simply what it appears to be, emergent from natural laws without the need for simulation. Yet the accumulation of anomalies, the lattice-like structure of space-time, the fine-tuning of physical constants, the behavior of quantum particles under observation, challenge this assumption. A purely materialist universe does not inherently explain these patterns. A computational framework offers a coherent narrative, connecting phenomena that otherwise seem disconnected. Leading physicists are beginning to take these ideas seriously,
James Gates, a theoretical physicist at the University of Maryland, discovered error-correcting codes embedded in the equations of supersymmetry, structures eerily similar to the algorithms used in digital computers. While not proof, it hints at the possibility that the mathematics underlying the universe may contain redundancies or constraints consistent with a computational substrate. Similarly, Juan Maldonado's work on holographic duality provides a mathematical framework suggesting that gravity, space, and time may emerge from underlying information. Theoretical research increasingly aligns with the notion that reality may have a programmable structure. The philosophical implications are profound. If the universe is computational, then consciousness may be an emergent property of complex information processing, not a mysterious, immaterial soul. Free will may exist within the constraints of the simulation, as a pattern of decision-making algorithms operating within parameters set by the program. Even death and identity could be reconsidered. If the substrate is informational, the self may be an organized set of data patterns, potentially reproducible or transferable under the right conditions. This framework also reframes cosmology. The universe may not be infinite or continuous, but discretized, constrained, and optimized for stability and computational efficiency. Its apparent randomness may mask an underlying order, a system running according to rules that preserve coherence across time and space. Galaxies, black holes, and cosmic expansion may all be part of a program, emergent properties of a computational process rather than accidents of nature. Ultimately, the theoretical framework unites philosophy, physics, and technology. It suggests that our universe, with all its complexity and beauty, is not arbitrary. Instead, it may be the output of an intricate algorithm, a simulation designed with constraints, rules, and perhaps even intention. This does not diminish the wonder of existence, it reframes it. We are not merely observers in a cold, indifferent universe. We are active participants in a computational reality, experiencing consciousness, choice, and meaning within a system far more complex than we can yet imagine. As we move forward, the question becomes not only whether the universe is a simulation, but what this means for the future. How might we test this hypothesis? What technologies, experiments, and discoveries could reveal the architecture of existence itself? And what might we learn if the universe is computational rather than purely material? And perhaps most intriguingly, how might humanity's own future mirror the processes we are beginning to uncover? If the universe is a simulation, then the frontier of science is not just to observe reality, but to interrogate the very code that may underpin it. What technologies, experiments, and discoveries could reveal the architecture of existence itself? What might we learn if the universe is computational rather than purely material? And perhaps most intriguingly, how might humanity's own future mirror the processes we are beginning to uncover? One avenue of exploration lies in high-energy physics. Particle accelerators like the Large Hadron Collider at CERN smash protons together at velocities approaching the speed of light, probing the fundamental building blocks of reality. Some theorists suggest that minute anomalies in particle interactions, energy distributions, or decay patterns may reflect underlying computational constraints. Just as a video game world might show artifacts when its engine is pushed beyond its limits, the universe itself could reveal glitches when observed at extreme energies or scales. Detecting such anomalies would provide empirical evidence for a discrete, programmed cosmos.
And yet, with each potential breakthrough, new questions emerge. If we are inside a simulation, what exists beyond it? Who or what runs the system? Is the program itself evolving, learning, or refining its rules? Could there be levels of reality beyond our comprehension? Nested layers of existence, each governed by its own computational substrate. The search for answers becomes not only a scientific pursuit, but an existential journey, one that challenges every assumption about life, reality, and the cosmos. Ultimately, the future implications of the simulation hypothesis are both exhilarating and unsettling. We are at the threshold of a new frontier, where observation, computation, and philosophy converge. The universe may not be a passive stage on which life unfolds, but a dynamic informational system waiting to be understood. And the more we explore, the more we realize that understanding the architecture of reality is not just an academic endeavor, it is a quest to uncover the deepest truths about existence itself. As we move forward in this journey, the evidence, the theory, and the imagination converge. The universe may reveal itself as a computational masterpiece, a simulation of breathtaking complexity where consciousness emerges naturally and the laws of physics are coded with intention. The discoveries that lie ahead may redefine our place in the cosmos and illuminate the profound question that has guided humanity for centuries: what is real? If the universe is a simulation, then we are confronted with questions that are as profound as they are unsettling. What does it mean for reality itself if the cosmos is a construct, a computational architecture designed to host consciousness and life? And if our universe is a simulation, what does that imply about existence, free will, and the ultimate nature of truth? These are the questions that blur the line between physics, philosophy, and metaphysics, the ultimate questions that have haunted thinkers for centuries. Consider the nature of consciousness. In a simulated universe, awareness may be a computational phenomenon, emergent from the processing of information. Each thought, feeling, and perception could be the product of algorithms operating beneath the surface of reality. Does this diminish the value of experience, or does it reveal an astonishing truth? That consciousness can emerge in any sufficiently complex system, whether physical, biological, or computational. The implication is both humbling and empowering. Our existence, while potentially artificial in origin, may still be profoundly meaningful within the context of the simulation. Then there is free will. If the universe is a program, are our choices real, or are they predetermined by the underlying code? Some theorists suggest that free will could exist within constraints, much like a character in a video game navigating a set of rules and probabilities. Decisions may be emergent, generated from the interaction of complex systems, rather than absolute or random. In this view, morality, creativity, and human agency are not illusions, but manifestations of computationally emergent phenomena, patterns of behavior arising from the rules of the system itself. The question of purpose arises inevitably. If a simulation exists, who or what runs it? Are we part of an experiment, entertainment, or a method of studying the evolution of consciousness? Perhaps the universe is a laboratory, a sandbox, or even a teaching tool for beings far beyond our comprehension. The scale and sophistication required for a universe simulation imply intelligence of staggering capability. But whether this intelligence is benevolent, indifferent, or ennoble remains a mystery. Quantum mechanics adds further complexity to these ultimate questions. The probabilistic nature of reality, the entanglement of particles across vast distances, and phenomena like quantum tunneling suggest a universe that operates under rules fundamentally different from classical expectation. Could these properties be signatures of computational algorithms, shortcuts and optimizations built into the fabric of the simulation? If so, then reality itself is malleable, adaptable, and contingent upon processes that transcend the limitations of ordinary perception. Even the structure of the cosmos, the fine-tuned constants, the lattice-like patterns at the Planck scale, and the strange alignment of cosmic structures hint at a design beyond randomness. These are not merely curiosities, they are clues. Clues that the universe may be an engineered system, optimized for stability, consciousness, and complexity. If this is true, then every discovery in physics, every breakthrough in cosmology, and every anomaly detected in quantum experiments is a window into the underlying architecture of existence. The ultimate paradox emerges when we consider nested simulations. If one civilization can simulate a universe, then it is conceivable that beings within that universe could eventually create simulations of their own. Each layer of simulation might be indistinguishable from its parent, producing a hierarchy of reality so vast and complex that the probability of inhabiting the base reality could be vanishingly small. In such a framework, every conscious being may exist simultaneously as a participant in multiple layers of reality, a concept that challenges our understanding of identity, causality, and existence. Time and space also take on new meaning. In a computational universe, these dimensions could be emergent properties, encoded as part of the simulation. And yet, with each potential breakthrough, new questions emerge. If we are inside a simulation, what exists beyond it? Who or what runs the system? Is the program itself evolving, learning, or refining its rules? Could there be levels of reality beyond our comprehension, nested layers of existence, each governed by its own computational substrate? The search for answers becomes not only a scientific pursuit, but an existential journey, one that challenges every assumption about life, reality, and the cosmos. Ultimately, the future implications of the simulation hypothesis are both exhilarating and unsettling. We are at the threshold of a new frontier where observation, computation, and philosophy converge. The universe may not be a passive stage on which life unfolds, but a dynamic informational system waiting to be understood. And the more we explore, the more we realize that understanding the architecture of reality is not just an academic endeavor, it is a quest to uncover the deepest truth about existence itself. The universe is vast. The mysteries are endless. The journey continues. And whether we are simulated or not, the experience of discovery, the thrill of wonder, and the pursuit of truth remain profoundly, undeniably real. As we step further into the question of simulated reality, the focus shifts from speculation to experimentation. Could humanity one day detect the code underlying existence? Could the universe itself yield its secrets to observation, computation, and inquiry? These are not merely abstract questions, they define a frontier where physics, information theory, and philosophy converge, opening the possibility of empirical tests that may reveal the architecture of the cosmos itself. One line of investigation focuses on the fundamental limits of space and time. If reality is computational, then the smooth continuum of the universe may be an illusion, masking an underlying discrete grid. The Planck length, roughly 1.6 times 10 to the 35th meters, represents the smallest measurable scale of space, and the Planck time, about 5.39 times 10 to the 44th seconds, marks the smallest unit of temporal measurement. Observing phenomena near these limits could reveal whether space and time are genuinely continuous or quantized, forming a lattice akin to pixels on a screen. High-energy cosmic rays and particle collisions at extreme energies are the most promising probes of these foundational scales. Subtle deviations in their behavior could provide the first hints of an underlying computational grid. Another approach arises from quantum entanglement. This phenomenon, where particles separated by vast distances instantaneously affect each other, seems to defy classical constraints, suggesting a level of coherence that transcends ordinary space-time. In a simulated universe, entanglement might be a computational strategy, a way for the system to maintain consistency across distant points without recalculating the entire universe. Future experiments designed to stress test entanglement could reveal inconsistencies, limitations, or latency effects that hint at a deeper structure beneath observable reality. The search for mathematical patterns embedded in physical laws is equally compelling. In 2010, physicist James Gates discovered error-correcting codes embedded in the equations of supersymmetry, structures remarkably similar to algorithms used in digital computers. These codes do not appear to serve a conventional physical purpose, leading to speculation that the universe itself may encode information in ways analogous to software. Further mathematical investigation could uncover additional patterns, redundancies, or computational features, providing a glimpse into the underlying architecture. Cosmology also provides tantalizing possibilities. Observations of the cosmic microwave background, the radiation left over from the Big Bang, reveal small-scale anomalies that do not fit neatly into existing models. These irregularities, temperature fluctuations, slight asymmetries, unexpected alignments,
could be interpreted as the resolution limits of a simulated universe, analogous to pixelation in a digital image. As telescopes become more precise and data collection improves, we may detect evidence that the universe is constrained in consistent ways with computational processes. The philosophical implications of these inquiries are as profound as the empirical ones. If the universe is a simulation, what responsibilities come with the knowledge that our reality may be constructed? How should we act, knowing that our choices, creativity, and consciousness are both emergent phenomena and potentially observable components of a larger system? These questions challenge conventional ethics, pushing us to consider morality not just within human society, but within the fabric of existence itself. Our actions may ripple not only through our immediate environment, but across a system of rules and algorithms that govern reality at its most fundamental level. Artificial intelligence offers yet another avenue. As humans create increasingly sophisticated simulations and autonomous agents, we gain insight into the conditions necessary for consciousness to emerge. By studying virtual worlds populated with intelligent, adaptive agents, we can better understand the computational requirements for self-awareness. This research has a dual purpose. It informs both our understanding of simulated consciousness and our capacity to detect patterns in our own reality that might indicate a similar computational substrate. If consciousness is an emergent property of complex information processing, then AI and simulation research may offer clues about the processes generating our own experience. Even art and creativity take on new meaning in this context. Patterns, symmetries, and emergent structures that appear natural may reflect algorithmic constraints rather than pure randomness. The beauty of a galaxy, the fractal complexity of a snowflake, or the elegance of a mathematical proof could all be manifestations of underlying computational rules. In this sense, exploration, creation, and imagination become more than human endeavors. They are ways of interacting with, probing, and understanding the architecture of reality itself. The nested simulation concept, or simulation within a simulation, further complicates the inquiry. If advanced civilizations can simulate universes, and if these universes can produce conscious beings capable of creating their own simulations, then layers of reality may exist beyond our perception. Each layer could obey rules similar to our own, or it might differ in subtle ways, producing a hierarchy of emergent realities. This concept challenges our assumptions of originality, causality, and identity. Are we inhabitants of a base reality, or participants in a nested chain of simulations so vast that comprehension is nearly impossible? Despite the philosophical complexity, practical experimentation continues to expand. Scientists are designing tests that could reveal computational boundaries, high-energy particle collisions probing lattice structures, entanglement experiments exploring non-local coherence, and cosmological observations targeting anomalies in the cosmic microwave background. As technology advances, these experiments may reveal hints of an underlying system, subtle clues that reality itself is informational and structured. The stakes of these inquiries are immense. Confirmation of a simulated universe would redefine physics, cosmology, consciousness, and even morality. It would challenge the way we perceive time, space, matter, and life. Conversely, failure to find such evidence does not diminish the value of exploration. It would refine our understanding of reality, narrowing the possibilities and deepening our insight into the extraordinary, often counterintuitive nature of existence. At the heart of this exploration lies a fundamental truth. Whether or not the universe is a simulation, the journey of inquiry transforms us. Each experiment, observation, and philosophical reflection expands the boundaries of human understanding. We probe not only the cosmos, but the essence of existence, challenging assumptions
exploring the unknown and embracing the mystery that drives science and imagination alike. As we continue, one principle becomes clear. The quest for understanding the universe is inseparable from the quest to understand ourselves. By probing the possibility of a simulated reality, we confront the nature of consciousness, the meaning of experience, and the scope of human potential. Every discovery is a window into the architecture of existence, every anomaly a clue, every question an invitation to explore further. The universe, whether simulated or organic, is a masterpiece of complexity. Its anomalies, patterns, and emergent properties invite curiosity, demanding that we continue to observe, calculate, and imagine. In the search for the underlying code of reality, we are engaged in an adventure unlike any other, a journey not merely through space and time, but through the essence of existence. As we probe deeper into the possibility of a simulated universe, the spotlight inevitably falls on consciousness, the singular phenomenon that defines our experience of reality. In a universe governed by computation, consciousness may not be incidental, it could be the mechanism through which reality unfolds. Every thought, every observation, every perception could play a role in shaping the simulated world, blurring the distinction between observer and observed. Consider the observer effect in quantum mechanics, where the act of observation appears to collapse probabilities into a definite outcome. In classical physics, the universe exists independently of observers, but quantum experiments suggest otherwise. The act of measurement seems to influence the system itself. If the universe is a simulation, this may not be a bug, it could be a feature. Consciousness may be the interface through which the simulation renders reality.
As we probe deeper into the notion of a simulated universe, the question becomes urgent. How could we test such a hypothesis? Until recently, simulation theory belonged largely to philosophy and speculation. But advances in physics, cosmology, and computational science suggest ways to approach the question empirically. While definitive proof may remain elusive, the pursuit itself reshapes our understanding of reality, consciousness, and the cosmos. One approach relies on detecting anomalies at the most fundamental scales of space and time. If reality is computational, then it is discretized, quantized, rather than continuous. Experiments using ultra-high-energy cosmic rays may reveal directional biases, lattice-like structures, or constraints indicative of a pixelated universe. Imagine observing the edges of reality where the simulation's resolution falters, revealing a subtle grid underlying the apparent continuum. Such patterns, if found, could provide the first direct evidence of a computational substrate. Particle physics offers another testing ground. The Large Hadron Collider, capable of recreating conditions fractions of a second after the Big Bang, probes the fabric of reality itself. Certain particle interactions, decay rates, or unexpected asymmetries might reflect constraints imposed by a computational system rather than purely natural phenomena. In essence, the universe may reveal its code under extreme conditions, much like examining the source files behind a complex program. Every collision, every high-energy interaction is a probe into the architecture of existence. Quantum entanglement remains one of the most fascinating clues. If particles are linked instantaneously across vast distances, it challenges classical notions of space, time, and causality. Some theorists propose that entanglement is a computational shortcut, a way for the system to maintain coherence without recalculating every interaction across the universe. Testing the limits of entanglement, pushing particles to greater separations, experimenting with decoherence, or probing correlations at unprecedented scales may reveal whether reality operates according to conventional physics or a deeper computational logic. Cosmology provides additional avenues. The cosmic microwave background, a relic from the early universe, contains subtle anomalies and asymmetries. Could these fluctuations be the pixelation of the universe, a signature of finite computational resolution. Observatories like the Planck satellite and upcoming missions aim to measure cosmic radiation with ever greater precision, searching for patterns inconsistent with purely natural processes. Even minor deviations from predicted uniformity could hint at a designed or computed cosmos. Mathematics offers an intriguing indirect test. James Gates's discovery of error-correcting codes embedded in supersymmetry equations raises the possibility that physical laws themselves encode information. These codes are strikingly similar to those used in digital computers to preserve data integrity. Further mathematical exploration may uncover additional structures, patterns, redundancies, or constraints that suggest an underlying computational substrate. In such a framework, reality is not only observed, but structured, an intricate blend of physics and algorithm. Nested simulations, the concept of universes within universes, introduce another layer of potential evidence. If advanced civilizations can create simulations, then statistical reasoning suggests we are more likely to inhabit a simulated reality than a base universe. Testing this hypothesis may involve examining anomalies, inconsistencies, or limits in observable physics. While these tests are probabilistic rather than deterministic, they offer a framework for reasoning about the likelihood of living within a computational system. Artificial intelligence and virtual worlds provide practical insights. By studying emergent behavior in complex simulations, we gain understanding of the conditions under which consciousness arises. Observing AI agents in virtual environments helps us comprehend how information processing generates self-awareness, decision-making, and adaptive behavior. These insights may inform our search for signatures of consciousness or computation in the larger universe. If the cosmos is a simulation, consciousness itself could be the key to detecting the underlying architecture. Despite these possibilities, challenges remain. Any test is constrained by the limits of observation, measurement precision, and our conceptual frameworks. A simulation, if sufficiently sophisticated, may be indistinguishable from base reality, making detection inherently difficult. Yet the absence of proof does not diminish the value of inquiry. Even the pursuit of these experiments expands our understanding, refines our models, and stretches the boundaries of science and imagination. The human dimension of this search is equally profound. By probing the possibility of a simulated universe, we confront questions of existence, purpose, and identity. Are we autonomous agents, co-creators of the simulation, or emergent patterns constrained by the architecture of the system? How do we interpret morality, creativity, and meaning in a universe that may be informational at its core? These questions transform the act of scientific inquiry into an existential adventure, blending physics, philosophy, and human curiosity into one single, ongoing exploration. Moreover, the search for evidence is recursive. As we refine experiments and develop more advanced technology, we may inadvertently approach the computational limits of the universe itself. Observations, measurements, and simulations conducted within reality are themselves part of the system, potentially influencing or interacting with the underlying computational substrate. In this sense, the act of inquiry becomes an experiment in its own right, a dialogue with the universe, probing the boundaries between observer and observed, cause and effect, reality and code. Even anomalies traditionally dismissed as statistical noise, coincidences, or quirks may gain new significance. Small, unexplained phenomena, whether in particle behavior, cosmic alignment, or quantum fluctuations, could be the subtle fingerprints of a system operating according to computational principles. Like the faintest brushstrokes in a vast cosmic painting, these details may reveal patterns invisible to casual observation, but profound in their implications. The implications extend beyond science. If the universe is computational, our understanding of consciousness, ethics, creativity, and even mortality is transformed. Life may not be arbitrary. It may emerge naturally from information processing.
Human experience, memory, and agency may be meaningful patterns within a system designed to generate complexity. Every decision, every insight, every act of creation becomes part of the ongoing computation of reality itself. Ultimately, the pursuit of testing a simulated universe is both scientific and existential. It combines empirical rigor with philosophical depth, demanding that we explore the limits of physics, mathematics, and consciousness while reflecting on the nature of existence itself. Each experiment, each observation, and each new insight brings us closer to understanding not only the cosmos, but our place within it. As we prepare to confront these mysteries, the question remains: will we detect the code of reality, or will it remain forever hidden? The journey itself is transformative, a testament to the boundless curiosity, ingenuity, and resilience of the human mind. Whether the universe is simulated or organic, the exploration illuminates the profound beauty, complexity, and mystery of existence, reminding us that the search for truth is as vital as the truth itself. As our journey through the universe's deepest mysteries nears its climax, we confront the ultimate ramifications of a simulated reality. The question is no longer theoretical. It shapes everything from the nature of consciousness to the fate of civilizations. If we live in a computational cosmos, then every discovery, every insight, every experiment carries profound implications for science, philosophy, and human understanding. Consider the nature of existence itself. In a computational universe, reality is not a fixed, immutable backdrop, but a dynamic system, continuously generated and optimized. Space, time, matter, and energy are not absolute. They are constructs of the simulation, rules imposed to produce stability, complexity, and consciousness. This reframes the very meaning of reality. What we perceive as solid, continuous, and objective may be, at its core, information manifesting according to algorithmic laws. Every particle, every force, every phenomenon becomes part of the program, a line of cosmic code running in real time. The consequences for consciousness are staggering. Our minds, our perceptions, our thoughts may be emergent properties of the simulation, patterns of information that achieve self-awareness within the computational framework. This does not diminish the richness of experience, it magnifies it. If consciousness is a feature of the system, then human awareness becomes both a product and a participant in the unfolding of reality. Our choices, creativity, and curiosity may not only exist within the simulation, they may actively shape it, influencing outcomes in ways we are only beginning to imagine.